phase part, we have phase is equal to G of j omega is equal to minus j upon omega, and you have 1 upon omega. If you convert it into phase using a formula, tan inverse of imaginary part upon real part, for this particular one, this is going to be tan inverse of 0 upon 1. Okay, so tan inverse of 0, which is equal to 0. And in the denominator, you are going to have tan inverse of omega upon 0. So that is tan inverse of infinity. That is nothing but 90 degrees. But this angle, so this is 0 degree and this is 90 degree. To this being this in denominator, when it comes in numerator, it has negative sign, right? So G of j omega is equal to minus 90 degrees. Now always remember, pole at origin will have magnitude contribution at as minus 20 log of omega and phase contribution as minus 90 degrees. Forget about this k here. What this k is nothing but n. Suppose you have two poles at origin instead of one pole. If you have two poles at origin, each pole is going to contribute minus 20 log of omega. So this is how you are going to get n into minus 20 log of omega, n times minus 20 log of omega. Okay, and that is why instead of k you can use n, because k might become confusing. Phase is nothing but each pole at origin is going to contribute minus 90 degree. If you have three poles, each pole will contribute minus 90 degrees. So minus 90 into 3. That is why it will become minus 270 degrees. So that is why it becomes magnitude is equal to minus 20 n if there are n poles at origin log of omega, and phase is equal to minus 90 into n. If you have a single pole, you will have minus 20 log of omega and minus 90 degrees. So this is the contribution of single pole at origin in the Bode plot. Similarly, if you have a 0 at origin, what you are going to get, everything similar but plus sign. Okay, so a single 0 at origin will contribute plus 20 log of omega for magnitude and plus 90 degrees for phase. Okay, is that clear now?
Yes.
Yes, all of you. I have unmuted you.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so what we have done here is magnitude and phase contribution of constant k that we have seen, and magnitude and phase contribution of first order factor, pole and 0 at origin. Always remember, if you need to remember it mechanically, always remember, if the factor is in the denominator, your magnitude and phase will have negative sign. If the factor is in the numerator, your magnitude and phase will have positive sign. Is that clear, all of you?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
So we will continue for some more time. I am just going to put it back. Now we are going to see factors, first order factor like s plus 1. Okay. Now suppose you have s plus 1. Suppose you have s plus 1. Sorry, pardon me. What happened? Now you have s plus 1 factor. You replace this s plus 1 s by j omega. So you are going to get j omega plus 1. And is this in the standard time constant form? Yes, because the coefficient that we have is 1. This particular format is known as standard time constant format. And if s plus 1 is in the numerator, you are going to call this first order factor in numerator. If suppose this is in denominator, then you are going to call this as first order factor in denominator. Now, the rule is same. If the factor is in the numerator, signs are positive. If the factors are in the denominator, signs are negative. But what the actual formula will be, let me put that back, screen back. Okay. Taking a bit time. Okay. So now let us scroll. Zeros at origin we have seen, right? We just have seen positive signs. Can you see this magnitude 20 log of omega, highlighted one, and phase will be plus 90 degrees. Okay, so zeros at origin will be similar to poles at origin with plus sign. Now, here, okay, first order factor. Now here, first order factor can be represented with the help of this equation. Now, if you have g of s is equal to 1 upon 1 plus st, s will be replaced with j omega, and so 1 upon 1 plus j omega t. Now to calculate magnitude of this g of j omega, obviously this is going to be in the denominator. So 20 log is common for the magnitude calculations. 20 log of magnitude of g of j omega. This is magnitude of g of j omega. Numerator is going to be 1 because under root 1 square plus 0 square, that is 1, upon under root 1 square, that is 1, plus omega square t square. So this is going to be the magnitude. Now, if you need to take it in the numerator, you need to mark it with negative sign. So this is going to be minus 20 log of under root 1 plus omega square t square. Okay. Now here onwards, we are going to have an approximation. Suppose this value, omega square t square, suppose this value is less than 1. First case, this value is less than 1. What this is going to be? Minus 20 log of under root 1. Because that will be, this portion will be negligible with respect to 1. So we can completely neglect it and we will consider only 1. So under root of 1 is 1. Log of 1 is equal to 0, right? So minus 20 log of 1, that is minus 20 into 0, that gives you 0 dB. Okay, I'll tell you the significance of that a bit later. Let us just first see the mathematical part. Okay, now when you have, suppose now you have omega t greater than 1. Now, if you have omega t greater than 1, what are you going to have? These are the square terms. So if omega t is greater than 1, omega square t square will certainly be too large than 1. So in that case, now you can neglect 1 and you will get under root of omega square square, which is nothing but under root of omega t. So minus 20 log of omega t. Okay. Now this is the formula that we will use for first order factor in the denominator. Okay. Now what the significance is, suppose omega t is less than 1. When omega t is less than 1, the magnitude is 0 dB. That means this particular factor doesn't contribute when omega t is less than 1. This factor will contribute when omega t is greater than 1. Okay. Now, see the example. We can see the example here. Yeah. Suppose your time constant, I'll give another example also. Suppose your time constant is 5. Sorry. Suppose your time constant is 5, say. Just a minute. Time constant t is equal to 5. What omega is going to be? 1 upon 5, right? 1 upon 5. So omega into t is equal to 1, right? When you multiply these two, omega t is going to be 1. So 1 is the threshold value. When omega t is less than 1, that means when t is 5, omega is going to be 1 by 5. When you multiply these two, you will get 1. So 1 is the threshold value. when omega t equal to 1 is the threshold. When omega t is less than 1, we saw on that screen that when omega t is less than 1, it contributes 0 dB. But when omega t is greater than 1, it contributes minus 20 log omega t. Okay, so this factor will not be contributing before omega t is equal to 1. Right? Now, what do you mean by omega t equal to 1? T is equal to, suppose we rewrite this equation. This equation will be t is equal to 1 upon omega, that we already know. So, when, or other way around, we can write omega is equal to 1 by. So, in your transfer function, suppose if you have s plus a 5 and you take this 5 common, you get 1 plus s by 5. In this case, what t is equal to according to standard time constant form? T is equal to 1 by 5. And so omega is obviously equal to 5. What we can say using this formula, just now what we have seen is before frequency 5, this factor doesn't contribute at all. And after frequency 5, it contributes minus 20 log of omega t. In this case, omega t is equal to 1 when omega is 5 and t is equal to 1 by 5. So that is why this frequency, which is a threshold frequency, before which this factor doesn't contribute, is known as a corner frequency. This frequency can be 5, 10, 2, 3, whatever, depending on the factor given in the transfer function. Okay, I hope this is clear now. Is that clear now?
Yes, ma'am.
Yes. Yes, ma'am.
Okay. Yeah. Okay. So now let us go back to the screen. This is the formula, corner frequency, what I was talking about. Okay. Now, always remember, this is an approximation, right? Because we have made this approximation, omega t less than 1, omega t greater than 1. When omega t will be greater than or less than 1, we have a threshold omega t equal to 1. Suppose now if t is equal to 1 by 5, omega will be equal to 5. If t is equal to 1 by 1000, omega will be equal to 1000. So what we can say, the frequency at which omega t becomes 1 is known as corner frequency, and at the corner frequency there is a threshold. Before corner frequency, that particular factor doesn't contribute 0 dB, and after that it contributes minus 20 log of omega t. Now see the this is all what we discussed just now. Phase of that. Phase is quite easy. This is the factor that we were talking about. Phase will be tan inverse of omega t. Now it will be omega t. Again, the approximation comes into picture. So before that corner frequency, it contributes 0. After the corner frequency, it